Okay, in this video, I'd like to discuss an example of the average theorem, the application of average theorem. Then I'm going to move to the next topic, which is going to be the derivative of real valued function. So let me first rewrite the statement of average theorem. Average theorem discusses the behavior of the power series at the boundary point of the radius of convergence. Okay, suppose f of x is defined by the power series that then goes from 0 to infinity, a(n) and x to the n. Okay, so this function is defined by the power series like this. And we're going to assume this power series has the radius of convergence. The radius of convergence is divided by r. And here we're going to assume this radius of convergence is positive and finite. That means r is positive and finite. Then we know this power series converges on an open interval centered at 0 and from minus r to r. In the open interval from minus r to r, the power series converges to a continuous function, right? But we do not know the convergence at both endpoints. We need to investigate the convergence at those two endpoints separately, right? And Average theorem tells us if the power series converges at those two endpoints, then the Average theorem suggests the value of that value of the power series. So if the power series converges, and x equals to the radius of convergence, then the value of this function or the value of this power series f is continuous. And the same statement is also true for x is minus. Okay. That means inside of the radius of convergence, in the open interval from minus r to r, we know the power series converges to continuous function like this. In addition to that, the average theorem tells us if the power series has a finite value at the endpoint r, then that value must be the limit of this continuous function. Okay? The value at the boundary point, when the power series converges at the boundary point, the value cannot be somewhere away from the limit of the continuous function defined in the inside of the domain. Okay, so this kind of value cannot happen. The power series. Actually, I'm not going to get into too much detail of the proof of average theorem. If you are interested in the proof of the average theorem, please consult the textbook. Rather than the proof, I'd like to think of the application of this average theorem. At first, let's consider the harmonic series. The harmonic series is given by the summation of 1 and 1/2, and 1/3, and 1/4. And we know this harmonic series diverges to infinity. Okay? You can check it using the integral test. But if we have the alternating sign, -1 to the n plus 1 over n, then when n is 1, we have plus sign, and the denominator is 1, and minus 1/2, plus 1/3, minus 1/4. Okay? And we know this value is finite. the series like that converges. Why? Since it is an alternating series. Okay, the absolute value of the general term decreases to 0. And we have the alternating sign, +1, plus and minus, and plus and minus. Any sequence, any series like that should converge. Okay, the question is, what could be the value for this series? Here, the value of this alternating series is actually log of 2. Okay, how can you compute? Or how can you obtain this value? That's the application of Average Theorem. To do that, let's consider the geometric series. Defined by the summation, as n goes from 0 to infinite, we're going to consider the geometric series x to the nth power. Then, this is going to be the limit as n goes to infinite. We take the finite summation as k goes from 0 to n. Okay, x. Then, this part is simply the summation of geometric sequence. And you can easily compute the expression of the summation of geometric sequence. It's going to be 1 minus x to the number of terms, which is n plus 1, over 1 minus x. Okay? And when you take the limit as n tends to infinite, this term, x to the n plus 1, converges to 0. And the whole expression turned out to be 1 over 1 minus x if the absolute value of x is less than 1. Okay? If the absolute value of x is less than 1, this term approaches to 0. Okay? So the power series, no, I should say the geometric series like this can be written as 1 over 1 minus x. Here x is the common ratio of the geometric series. Okay. That's a power series. A simple power series whose coefficient, the coefficient sequence is always 1, right? And for the power series, we know we can apply the term-by-term integration and the term-by-term differentiation inside of the radius of convergence. Okay, so let's apply term-by-term integration. If we compute the term-by-term integration of the geometric series like this, we're going to get the summation as n goes from 0 to infinite. Okay, what's the integral of x to the nth power? We're going to have 1 over n plus 1 and x to the n plus 1. This will be the same as the integral of right-hand side, which is 1 over 1 minus x. Actually, you can rewrite this as the integral from 0 to x and 1 over 1 minus t dt. And we know how to compute the integral of the function like this. Okay, it's going to be minus log of 1 minus t. Okay, and we evaluate this from 0 to x. Okay, so when you put 0 for t, you're going to have log 1, which is 0. Okay, so this expression can be written as minus log of 1 minus x. Or log of 1 minus x can be expressed as minus. If you move this minus sign to the other way around, we're going to have the summation that then goes from 0 to infinity 1 over with this 1 over n plus 1 and x to the nth power. And this identity is true for x for that the value is less than 1. Okay. Now, from this identity, what if we replace x by minus x? Then log of 1 plus x can be expressed as minus the summation as n goes from 0 to infinity. Here we have I'm sorry, because before we move on to the further computation, we have to modify the index for this expression. Here, this expression is actually I forgot to put plus 1 here, and this expression can be written as instead of n plus 1, the index by using the index shift, you can rewrite this as 1 over n and f to the n plus 1, f to the n. Okay, here the index n starts from 0. And if we apply the index shift like this, you can modify the range for the index n from 1 to infinity. Okay? Then, in this, I'm going to replace x by minus x in this expression. That's going to be the summation as n goes from 1 to infinity. We have minus 1 to the n. We have minus x to the n over the quotient n. Okay, which can be written as the summation as n goes from 1 to infinity. We have minus 1 to the n, and we have one more minus sign. Okay, that can be expressed as the sign like this: minus 1 to the n plus 1 over the denominator is n, and we have x to the n. Okay. This expression can be understood as x minus when n is 1, we have x, and when n is 2, we have minus sign, and x squared over 2, and x cubed over 3 minus x 4 over 4. Yes. And you know, this series converges at x equals to y. If you put 1 for this series, it's going to be alternating series. Okay, so we can apply the average theorem. We can apply the average theorem. This the function defined in this expression is continuous at x equals to 1. That means the alternating series as n goes from 1 to infinity minus 1 to the n plus 1 over n. Okay, we have seen this series converges from minus 1 to 1. Right? The radius of convergence of this series is 1. And you know the series converges at x equals to 1. So this is going to be the power series. The coefficient is given by this one. and x to the nth power. Okay, the value when x equals to 1, the value of this series can be obtained by, since it is continuous, this value can be obtained by the limit of this power series as x tends to 1 from the left-hand side. So this is the left-hand side. Okay. And we verified power series inside of the radius of convergence. This power series is the same as log of 1 plus x. Log 1 plus x. And we know log function is continuous. So this is log of 2. Okay, when you take the limit as x tends to 1, you're going to have log of 2. That's why we have this value, log of 2, for the alternating series like that. But we have seen the harmonic series. This harmonic series diverges to infinity. Okay, so you cannot apply the Average theorem to this power series. Let's consider the geometric series itself. The geometric series, summation x to the nth power, is obtained by 1 over 1 minus or the radius of convergence 1. Okay? Yeah. And x equals to minus. Okay? If x is 1, then this series diverges. This function diverges. However, when the left hand boundary minus 1, the function 1 over 1 minus x is continuous. Continuous, and take the value, okay, if you put minus 1 for this value x, the variable x, we're going to have 1/2. That doesn't tell us the series minus 1 to the nth power as n goes from 0 to infinity. Okay, and you put x equals minus 1 to this power series. That's not going to be 1/2. Why? Since this type of power series does not converge, okay? The series does not converge. So you cannot apply the Average theorem to this type of power series. Okay, that's a nice application of Average theorem. Now I'd like to move to the next topic. Actually, I'm going to move to the next chapter. That's on the differentiation. So, in section 28, we'd like to develop basic properties of the derivatives. So when we first define the derivative of a function, of a real valued function, here f is a real valued function on open interval that contains point of interest A. Then we're going to say this function is differentiable. Differentiable at A. If you can compute the derivative, okay? How can you compute the derivative of function f at A? As you already know, the definition of this derivative. The derivative will be defined by the limit as x tends to A. The limit of mean rate of change, f of x minus f of A over x minus A. Okay? So, differentiability can be defined by the existence and finiteness of this value. So, this limit exists and finite. Okay, we're not going to say this function is differentiable if this limit diverges to infinity. Right? The differentiability will be defined by the existence and convergence to a finite value of this expression. In the whole definition of differentiability, we simply assume a real valued function and the existence and finiteness of this value prime of A. Okay? I'd like to concentrate on the continuity condition of this function. Here in the whole expression of the definition of differentiability, we do not mention anything on the continuity. But if the function f is differentiable, and the value at a point A, that means this limit exists, then the continuity is also true under this assumption. The function f is continuous. The differentiability can be understood this way. Then what about the continuity? The function f is continuous. That means the limit of f of x as x tends to A is the same as f of A. Okay. Of course, we have defined the continuity using epsilon and delta, but the essential meaning is this one. Okay. The limit as x tends to A is the same as the value of the function at that point. All right. Why do you have this implication? The function f of x can be expressed using this quotient f of x. It's better for me to write this one first. You have x minus a, and multiplied by this quotient f of x minus f of a over x minus. Okay. For x is different from a, you can use this quotient or division expression like that. And if that's the case, you can cancel those terms to get f of x and minus f of a. So to recover the f of x, you need to add up this quantity. Okay? This is always true except when x is a. Okay? So what if we take the limit of both sides of this expression as x tends to a? The limit of function f of x is obtained by the limit as x tends to a. We have x minus a, and f of x minus f of a, and x minus a, and plus f of a. Okay, the limit of this whole expression can be split into this way. At first, this constant summation f of a can be moved out of the limiting process. And the limit of the product of two expressions can be obtained by the product of individual limits. We first take the limit as x tends to a, or as x tends to a of the expression x minus a, multiply by the limit as x tends to a, f of x minus f of a over x minus a. Okay, we can split the limit of product of two expressions if those two, both of these two expressions, both of these two limits exist. Okay, yeah, we assume the differentiability. That means this expression converges to f prime of a, which is a finite number. And this expression converges to 0. So the product of 0 and some finite number f of a turn out to be 0. So the whole expression should converge to f of a. That means the function f is continuous at that point. Right? So the differentiability automatically implies the continuity. You don't need any additional continuity assumption. All right. Now let's discuss some basic formula for the differentiation of real-valued function. Assume all functions log are differentiable and x equals to a. First, the constant multiplication. We have f, the function f, multiplied by a constant c. The derivative of constant multiple evaluated at a will be c times f prime of a. Okay, and sum of two different functions. The derivative of sum of two functions can be obtained by the sum of their derivatives. Say suppose we have sum of two functions, f and g. If you compute the derivative of this function at value a, that's going to be the sum of f prime of a and g prime of a. By combining those two properties, we know the derivative is linear. Okay, the differentiation has the linear property. The linear combination of two differentiable functions can be the derivative of linear combination of two functions can be obtained by the linear combination of their derivatives. That's the linearity. All right. And the fourth formula are the derivatives for the product and the division of two functions. I think all of you know how to compute the derivative of product. If you take the derivative of product of two functions, excuse me, the derivative of product of two functions can be written as f of prime of a multiplied by g of a, and plus f of a and prime g prime of a. Okay. That's the Leibniz rule. All right. And also, the derivative of division f over g should be written as f prime of a and g of a minus f of a and g prime of a over g of a squared. Okay, those are the first few important formula for the differentiation. And the next one, the next important formula is the chain rule. Chain rule is the way to take the derivative of composite function, the composition of two functions. Let's say f is differentiable and x is a. And there's another function, g. This function is differentiable at f of a. That means the domain of definition of second function g include the point, the value f of a. If that's the case, you can take the composition of these two functions, g of f. Okay, and this function g of f is also differential. X is a, and chain rule. The chain rule tells us the way to compute the derivative of this composite function. The derivative of g of f, derivative of a, can be obtained by you first take the derivative of outer function g prime f of a, then take the product with the derivative of inner function. You take the derivative of f. Okay, I think all of you already learned this chain rule. Okay, this is the chain rule for a single variable, real valued function. Okay, I think you have learned this property from the high school mathematics and the calculus 2. Okay, so I'm ready to move to the next section, the mean value theorem. Okay, the first theorem that we're going to deal in this section is okay, something like this. If we have those three conditions, then the conclusion is the derivative of this function at x naught is 0. For the function f is differentiable. To do that, we first need to the function the domain of definition of this function include the point of interest x naught. So this function is defined on an open set or open interval that contains x naught. And the function f is differential at point. Okay, so the first condition tells us x naught is not the end point. Okay, it is included in the open interval. Okay, that means x naught is not the end point of the domain. of the domain or the domain of definition. And finally, the third condition is the function f x is maximum or the minimum or its minimum at x naught. If that's the case, the derivative at that point must vanish. It should be zero. Uh, for many cases, it's very important for us to compute the maximum or the minimum of certain function. Okay, and this theorem tells us the candidate points of the maximum or minimum of real valued function. Okay, before we discuss the proof of that property, let's consider this fact. You want to find the maximum or the minimum of a continuous function on an interval. Okay, that's a very natural problem that we're going to encounter in a real-world application of mathematics, in an engineering problem or physical problem or even economical problem. It's very important for us to compute the maximum or minimum of certain function. Okay, we want to minimize the cost or we want to maximize the profit. Okay, so we are given a continuous function whose domain is an interval. To find the maximum or minimum, if we have these three conditions, the maximum and minimum point should have this property. The derivative at that point must be zero. Okay, so we need to investigate the points there. Okay, f prime. Okay, if you have all three of these conditions, the maximum or minimum point has vanishing derivative. So you need to compute, you need to investigate a point where its derivative is zero. Okay, but some function defined on a closed interval may not have a vanishing derivative at the minimum or maximum point. Okay, if the function defined on this interval may goes like this. Okay, so the minimum appears at that point. Okay, the derivative at that point. This is a non-differentiable point. Okay, and what about the maximum? The maximum actually realized at the end point of the domain. Okay, so in this example, the both the neither of the maximum nor the minimum has vanishing derivative. The function is not differentiable at this point. Okay, and at this point, you cannot deal with the both side derivative. You can only compute one side derivative at that point, since it is the end point. of the domain. So you want to find out the location of the maximum or minimum. You need to investigate the point where the derivative vanishes, or the function f is not differential. Okay, you need to investigate non-differential point and the endpoints of the domain of the interval. Okay, so those three types of points are the candidates for the maximum or minimum points. So let's consider the proof of this property, this theorem. So the function f is defined on an open interval from a to b. There x naught. This point x naught is somewhere in the open interval. That means x naught is greater than a and less than b. And we're going to consider two cases. Either the function takes its maximum or minimum. Here, for the simplicity of the proof, we may assume the function f as its maximum value at x naught. For the minimum point, you can use the same proof with minus. Okay? And the function f has the minimum point. The function minus f obtains the maximum. And the derivative, the vanishing derivative for f of x and minus f of x. Both of them should be 0. Okay. Okay, in addition to that, we assume the derivative f prime at x naught. Okay, we need to conclude this value must be 0. Okay, so here, what if we assume this is non-zero, or even it is positive? Under this assumption, I'd like to derive a contradiction. So suppose the derivative of f at x naught is positive. F prime x naught. This value is obtained by the limit as x tends to a, x tends to x naught, f of x minus f of x naught, and divided by x minus x naught. Okay, so this limit converges to a positive number. Then there exists delta, positive delta, such that okay, here in an open interval from a to b, we have a point of interest x naught. Okay, and when you take the limit as x tends to delta 0, this expression converges to a positive constant f prime at x naught. Okay, so since it is positive, we can choose a small delta such that if x minus x naught this difference is smaller than delta. That implies our expression f of x minus f of x naught. Okay, since this quotient converges to some positive constant, this expression is positive. Of course, this expression is meaningful when x is different from x naught. That means we need to exclude the case when x is the same as x naught. Okay. In addition to that, the function f is defined only on this interval from a to b. So even if it is true, you cannot choose this delta big enough. Okay, you cannot choose this delta as big enough like that. Okay, so the domain of definition is the interval from a to b, right? And x naught minus delta, x naught plus delta, the interval centered at x naught of radius delta should belong to the interval from a to b. That's the domain of definition. Okay. So here, for the point x naught, the derivative of function is positive. Okay, that means the derivative, the function actually has a tangent line whose slope is positive. For such a case, here we have x naught and radius delta and minus delta. Since the derivative is positive, we have this inequality for x, all the x that belong to this interval. Okay, from minus x naught minus delta to x naught plus delta. You have that inequality. So we need more space. So if we select x, okay, if x, the right side of x naught, if we look at x in x naught and x naught plus delta, then this x minus x naught is the denominator is positive. That means the numerator is also positive. Okay, f of x minus f of x naught is positive. In other words, f of x is greater than f of x naught. That means the function f, cannot take the maximum. Here, that's our assumption. Okay, so if the derivative is positive, the function f cannot take the maximum. That gives us a contradiction. Similarly, if the derivative is negative, we get a contradiction. So the derivative at x naught, at the maximum point, the derivative must be 0. Okay. All right. Actually, you have learned the sequence of theorems of the derivatives, such as Rolle's theorem and the mean value theorem in the high school mathematics. But now, in high school mathematics, we do not have a chance to read through the proof of that theorem. Here, I'd like to give you the proof of Rolle's theorem and the subsequent mean value theorem. Rolle's theorem states like this. The function f is continuous on a closed interval and differentiable in open interval. Okay? Actually, the differentiability guarantees the continuity. So the second condition, differentiable on this open interval from A to B, also implies the continuity of the function in an open interval. In addition to that, we need a continuity at both endpoints. So the first condition actually tells us the function f is continuous at those two endpoints. Right? Moreover, if the value of this function at those two endpoints are the same, f of a is the same as f of b, then there exists some point x in this open interval such that the derivative vanishes. Okay? In the previous theorem, we have seen that the derivative of certain function must be zero if the function attains the maximum or the minimum. Okay? So from the conditions or assumptions of the Rolle's theorem, you need to show the existence of either maximum or minimum x inside of the domain. Okay, since we have a continuous function over a closed and bounded domain, since f is continuous, a closed interval, and this interval is closed and bounded. A continuous function has a very nice property over a continuous function defined over on a closed and bounded interval has a nice property. You can always guarantee the existence of maximum and minimum, right? F as a maximum and a minimum. So there exists x naught and y naught in the closed interval from A to B such that f of x naught is the minimum and f of y naught is the maximum. That means f of x or x, the closed interval from A to B, f of x is greater than or equal to minimum value and less than or equal to the maximum value. Here, our claim is either one of them. either x naught or y naught is actually inside of the open interval from A to B. Okay, inside of the open interval. Okay, that means if both x naught and y naught are both endpoint of the interval from A to B, that means x naught is A and y naught is B. Or for the other way around, x naught is B and y naught is A. For both cases, f of A is the same as f of B. That's our assumption for Rolle's theorem. Okay? If those 2 points, the maximum point, x naught is the minimum point, the minimum point and maximum point are both endpoint A and B. And the Rolle's theorem assumes those two values are the same. That means the function f over the closed interval from A to B has the same maximum and minimum. The maximum value is the same as the minimum value. That means the function is constant. Okay, so if that's the case, f of x is the same as the boundary point, the boundary value for all x. So f, the derivative is actually identically zero since it is a constant function. Then this conclusion is true. Okay, any point in this open interval, the derivative is zero. So you're done. Okay? Otherwise, that means the function f is either is x naught, the minimum point and maximum point are not the same as the both endpoints. That means the function f is either mean maximum or minimum at some x in the interior, inside of the open interval. Okay, not at the boundary point. Okay, then the derivative at that point. Okay, and minimum point or maximum point, the derivative must be zero. Okay, that's the proof of the Rolle's theorem, and you can easily generalize this situation to the mean value theorem. Or MVT in short. Here, the condition for function f is the same as before. Function f is continuous on the closed interval, and the function is differentiable in open interval. We do not have the equality condition of the value at the end of the limits. Okay. Under this assumption, the mean value theorem tells us the existence of point x in the open interval such that the derivative at that point is the same as f of b minus f of a over b minus a. Okay? Excuse me. So let's consider the function defined over the closed interval from a to b. the function may go like this. And what about the right hand side? This expression is the mean rate of change of the function f over the interval from a to b. Okay, the mean rate of change. Then what about this one? The derivative. Derivative is also considered as the rate of change, but it is evaluated instantaneously. Okay, this is instantaneous rate of change. Okay, the mean rate of change, the right hand side is the slope of this straight line that connect the starting and end point of this function. Okay, and mean value theorem tells us the existence of a point, the existence of point x, whose derivative or the rate of tangent line, the slope of the tangent line is the same as the slope of the line segment that connects those two endpoints. Okay, that's the mean value theorem. Okay, how can you verify this property? Okay, let's say Lx is the linear function connecting both endpoints of the graph. That means L of x is given by f of a plus the slope of this straight line will be f of b minus f of a over b minus a multiplied by x minus a. Okay, so if you put a for x, you simply, since this term is 0, you simply get f of a. And if you put b for the variable x, this b of a will be cancelled with each other to get the whole expression out to be f of b. Okay. Moreover, it is a linear function, the first order function with respect to x. That's a straight line or line segment connect those 2 points. Then, and prime of x, the derivative is simply the coefficient of the linear term x. It's going to be f of b minus f of a over b minus a. That's the left hand side. No, I should say the right hand side of the mean value theorem. Now, let's introduce another function g. It's going to be defined by f of x minus this straight line, f of x. Then, the function L is a linear, it is a very nice function, okay, continuous and differentiable. And the condition for the mean value theorem assumes the function f is continuous on the closed interval and differentiable on the open interval. So the function g defined in this way inherits all those conditions. This function is also continuous on a closed interval and differentiable on an open interval. Moreover, or is g of a. Okay. This function, L of a, if you put a for variable x, you're going to get f of a. That means if you put a for this variable x, you're going to get f of a minus f of a, which will be 0. And also, g of b is 0, too. If you put b for variable x here, okay, you're going to get f of b. So g of b will be f of b minus f of b. Okay? Then this new function g satisfies all the conditions for the Rolle's theorem. Is continuous on a closed interval and differentiable on an open interval, and the value at those two endpoints are the same. So you apply Rolle's theorem to the new function g, derivative x in an open interval, such that g prime of x is 0. And this g prime of x can be expressed as f prime of x and minus f prime of x. In other words, f prime of x is the same as L prime of x, and you know the L prime is the slope of this straight line will be the mean rate of change, f of b minus f of a over b minus a. Okay, that's the proof of mean value theorem. And there are few straightforward consequences of this mean value theorem. If you have differentiable function and the derivative is identically 0, the function f is continuous. No, this is a constant function. F is a constant. Okay, actually only we know this property. If the derivative is 0, identically 0, the function itself is a constant. But how do you prove this simple property? Yes, the proof relies on the mean value theorem. Okay, suppose this function f is not a constant function. We're going to derive a contradiction. Okay, if it is not a constant function, there exists 2 points, x1 and x2. Okay, x1, x2, they are different. And both of them belong to the interval from a to b. That's the domain of definition. But f of x1 is different from f of x2. Okay? So if you apply the mean value theorem to function f on the interval from x1 to x2. Okay? If you apply the mean value theorem to this closed interval, to get there exists x in an open interval from x1 to x2, such that f prime of x is given by f of x2 minus f of x1 over x2 minus x1. Since their values are different, this quotient is non-zero. Okay? That contradicts to our assumption that the derivative always varies. Okay? Another straightforward consequence of this mean value theorem, or actually the corollary to this property, if you have two differentiable functions and the derivative, their derivatives agrees. Okay, then If two functions have the same derivative, are they the same? No, they have constant difference. Okay, there exists a constant C, such that f of x is g of x plus some constant for all x in the domain of the function. Why? You can apply the previous corollary to the difference option. Okay, since the derivatives are zero, f, the derivative of f minus g is identically zero. That means this function f minus g is a constant function c. Okay. Uh, okay, I think that's pretty much everything that I have to say in this video. So let's call it a day and see you next class.